Welcome to our first webinar of the year, which you can tell it's the first because it's a little having some trouble this morning. But okay, so I'm Heather Ashenveld. I'm a program manager in the MAPP program, and I have some more introductory material, but I don't want to waste any more time with that. So I want to just jump into introducing our first speaker. And the first of 3 speakers on this topic of unified modeling across scales. So this is David Walters from the Met Office, and David is a scientific manager for the Global Atmospheric Model Development Team at the UK Met Office, and this team is responsible for maintaining and developing global atmosphere configurations of the Met Office's unified model to be used seamlessly across all timescales. David and his team work in collaboration with other Met Office teams to translate scientific developments into improvements to the global atmospheric model. They assess model performance across different timescales and its sensitivity to both new model formulations and uncertainties in physical parameterizations and numerical formulations. This approach results in global atmosphere configurations to be used in a consistent manner for applications from global weather forecasting for the next few days or weeks through seasonal and decadal forecasting, and even out to climate research experiments that last hundreds of years. David has worked on atmospheric model development since he joined the Met Office in 2004, and he has managed the Global Atmospheric Model Development Group since 2010. And he received a PhD in theoretical physics from the University of Wales, Swansea, and David is speaking today on seamless development for weather and climate prediction for the Met Office's unified model. David, thank you very much for joining us today, and I see that your screen is up, so you can just put it in presentation mode and go ahead when you're ready.
Brilliant, thank you. Okay, so thanks for joining me this morning, this evening, this afternoon, wherever you are. So today I'm going to talk about seamless model development for weather and climate prediction, and I will start by giving a quick introduction to the Met Office and the unified model, and then I'll move on to describe our global atmosphere configurations that we develop. I'll talk in some detail about how we go through the model development, and I'll try and focus on what we see as the most significant benefits and some of the costs that are associated with this as well. And hopefully I'll persuade you that the benefits of seamless prediction outweigh the costs. And just to come back to the introductory slide here, you can see that I've got a reference here. It's worth following this up. So this is a paper by Andy Brown, who's the Met Office Director of Science, and this was on exactly this topic, published in BAMS in 2012. So the Met Office are the UK's National Met Service, and we're responsible for delivering weather and climate predictions and advice for a range of customers, including the UK public, including the UK government, government agencies, including the Ministry of Defence and the Armed Forces, as well as commercial organisations in the UK and abroad. And to do this, we need to provide advice across a wide range of timescales, from the next minute, or what's just happening right now, right through to centennial climate information. So the main modelling tool that we use for this is the Met Office Unified Model. And this was first formulated in the early 1990s. At the time, this was developed by consolidating code from our previous modelling systems that were completely separate and pulling them into one code base that could be used for global coupled modelling, NWP modelling, and mesoscale NWP modelling. This gave some immediate benefits by improving the performance of the mesoscale model by pulling through improved parameterizations that were in the climate model, but straight away they were seen as compromises that had to be made at this stage. For example, the previous mesoscale model was non-hydrostatic, and the first unified model was a hydrostatic model, and they had to wait almost 10 years to have a non-hydrostatic model again. Today, the unified models are a very flexible atmospheric modelling code. It's used for a wide range of applications. So within the Met Office, in terms of our products and outputs, we do centennial climate change experiments as part of CMIP exercises using the coupled to ocean and sea ice models at resolutions of about 130 to 60 kilometres. And we have a seasonal forecasting system, ensemble prediction system, deterministic global NWP. We tend not to do any regional scale NWP anymore with kind of 12-kilometre resolution, because our global models approaching this resolution will soon be overtaking that. But our highest resolution operational model is a 1.5-kilometre resolution convection permitting model, which is called the UKV, although we do also have a 300-metre model which runs in research mode over London and Heathrow Airport. So there's the problem right away. We have to basically be able to support a single model that runs across all of these time scales and all of these spatial scales. So if we think about the horizontal resolution, as I just said, our highest resolution is about 300 meters. There's a factor of between about 100 and 1,000 with 100-meter, 300-meter resolution models and what we're running for global NWP out to global climate change experiments. And we have to have a dynamical core that will work across all of those scales, and ideally model parameterizations that work as well. So the current dynamical core is called Endgame. This is still formulated on a regular latitude-longitude grid, and this is something that essentially comes from our unified framework. So at the point of putting the model together, this was seen as the best grid to use because it could be used for limited area models and for global models. It's a non-hydrostatic model with a deep atmosphere. It uses semi-implicit, semi-Lagrangian formulation. There's a range of physics options that can be used, physics parameterizations. When we're running global modeling, we run with a convection scheme. When we're running higher resolution, 1.5 kilometer models, the convection scheme switched off. It's almost always coupled to a land surface model, but it can also be coupled to ocean models, sea ice models, chemistry and aerosol models, and other models for when we're doing things like Earth system modeling, it'll be coupled to ocean biogeochemistry and those sorts of additional extra complex processes. So since this original formulation of the it has been recognized by the community that there are synergies between NWP modeling and climate modeling. And if we look at these modeling suites, focusing here on the global model, essentially we're looking at more or less the same model formulation, but set up in runs going across a range of timescales and resolutions. So many of the model characteristics that we see in a day one forecast are also present in the long climate change runs and vice versa. It's not universally true, but it's true of many of them, especially if you manage to formulate the model in a similar way. So in recognition of this, the climate modeling community will increasingly run short runs of their climate model using either data assimilation or starting from an independent analysis to study the growth of model error and to confront the parameterizations with real high-quality observations. And an obvious example of this is the transpose AMIT framework. Shorter forecast range, NWP centers are increasingly running their models out to longer timescales than they produce forecasts for in order to confirm whether they have a reasonable climatology. And again, it's seen that if you can have a model that produces a good day one forecast and has a reasonable climatology, then that's much better than one where the climatology drifts off into an unrealistic state. So the Met Office is obviously well placed to take advantage of these synergies because we already produce and have systems that produce forecasts and projections across all of these timescales. And for a long time, this is something that we've been taking advantage of by having a dynamics team and physics development teams that try and produce their parameterizations and their outputs for use on all of these systems. But until fairly recently, 5 years ago or so, we had separate teams that pulled together the final configurations and made them operational. Those teams in the climate and weather side would try and work together to make sure that major parameterizations that provided benefit in one could be pulled through to another. But this sometimes caused difficulties. If something had already gone into one model and caused problems in the other, it caused a tension, and it would take a reasonable amount of time to resolve. So the final step, which we took from the atmosphere about 6 years ago, was to move towards developing a single scientific configuration that could be used at all timescales. So we call this our global atmosphere, or GA configuration, and it's essentially a set of physics and dynamics options within the that can be used across a range of resolutions. And by global, what we really mean here is non-convection permitting resolutions, so anything that's running with the convection scheme, and this is global models from 135 kilometer resolution out to 10 or 12 kilometers, and those could be global models or regional models. And it's designed and tested on timescales from day one out to hundreds of years. So we'll try and go through in detail now our development process to try and explain how we make changes to the model and ensure that we are getting all the benefits that we can. The majority, well, all of our model developments start in what we call the continuous research cycle. And essentially this is any piece of work that's using the unified model, ideally using one of our GA configurations, but this can include multi-year projects such as the development of a new dynamical core or a new physics parameterization scheme. It can involve smaller projects such as a PhD that somebody's doing looking at a particular process and improving the representation of that process, right down to somebody sat at their desk running a basic set of parameter tests and looking at the sensitivity to changing one parameter. All of this is seen as continuous research cycle work. So that's all bottom-up model development, but the research cycle also includes top-down model development, and by this we mean model development's looking to address something in the model formulation. So we have a range of groups called process evaluation groups, and these are formed to try and improve specific model problems, what we see as our major model problems. We put together a group of scientists, and we give them several years, and at least one person there is given the majority of their time to spend on this problem, and try and understand the real cause of the problem, the underlying cause of a problem, and how we should go about dealing with it. This research cycle work includes engagement with a wide range of partners, both in academia and in operational centres in the UK and across the globe. And we think that this research cycle is probably the best point at which to do that collaboration. It becomes very difficult when you're doing a run and then you want to look at the results, and then the next week you want to make a decision when you're in the kind of implementation stages. But we find that collaborating in this research cycle gives us space and room to do that collaboration and to get the most out of it. And so before we even think about a unified configuration, we can see the benefits of a unified modeling system here, in that any work that's taking place here is teaching us something about our model and something about how we can improve our modeling systems, even if that work is motivated or funded by a single application or a single customer. So my team's job is to put together these GA configurations, and we label these with numbers, GA1, GA2, GA3, and these are released in what we call a roughly annual timescale. So this is somewhere between a year and 2 years in moving from one GA release to another. This work starts before the release of the freeze of the previous release, where we plan which changes we want to pull from the continuous research cycle into the implementation cycle. So this is essentially an identification of which changes are mature enough and ready to go in, as well as coming up with a list of changes. We prioritize these changes, and we think about and define what we say the scope is, what the limitations are, and what the timescales are for the freeze, and we give ourselves some deadlines. Every change that we want to build in has to go through a set of standard tests, and we ask the model change developers themselves to run these tests. So we give them controls, and they will run currently a set of, they'll run a 20-year atmosphere and climate simulation, and they'll run a set of 6-day NWP forecasts spread out over 2 years in time. And we give them a framework in which to assess the results of those tests as well. So you'll notice that there are arrows here going back from the release cycle into the research cycle. So if there are major problems with a change, this will be pushed back into the research cycle. If there's time to deal with this within the release cycle, we will try and do that. But especially for the lower priority changes, if it starts causing problems, then it will be pushed back into the research cycle for the developer to improve it for the next release. At the end of this, assuming that the performance is reasonable, the changes are documented and passed over to my team for review. We review the documentation, we review whether the code is suitable and on its way back into the, if it's any new code, back into the code base. And if it's a change that has a significant impact, we pass it through a process called science assurance, where they have to, the developer has to present their change to an audience of scientists who then are encouraged to ask as many questions as possible about what they're doing, why they're doing it, alternative things that they could be doing, and that can either get to the point of the change being rejected because it causes some significant problem, to the maybe some additional tests being run, so they might be asked to do some coupled runs or some runs with data assimilation if they think that's particularly important, or looking at runs at different resolution. Or it could just lead to the change being passed through to what we call package testing. At some stage, these changes will get through to package testing, and at this stage, my team is responsible for building these changes together in packages, for repeating these standard tests, and also running tests of increased complexity. So we'll start running higher resolution and coupled climate model runs, NWP runs with data assimilation, and maybe some ensemble prediction runs in here as well. You'll notice there's arrows in 2 directions up here. So yes, again, changes, especially lower priority changes, may be pushed back into the research cycle if they start causing problems. But we also leave open the possibility of pulling changes into the release cycle. So if there's a particular problem that we find in package testing, and there's a change in the research cycle that we believe will address this, if it wasn't mature enough here, but is mature enough here, we'll pull it through into our release cycle. We chill these configurations, which means we think they're pretty much ready, and then we go through a tuning phase. And this will be a tuning of individual phenomena like dust uplift or the source term for non-orographic gravity waves, but it may be tuning for emergent properties as well, such as the top of atmosphere radiation balance. Once we've frozen the configuration, this is then assessed in a series of longer runs. So we'll run, say, hundreds of years of climate integrations, couple of climate integrations. We'll run higher resolution NWP tests, maybe with more sophisticated data assimilation. We'll run systems that we can't afford to run back here as well, like our seasonal forecasting system. And we'll use all of these together to try and assess the performance of the model. So the results are then sent out to our collaborators and people that we work with to assess. We pull together the results, and at the end of this, we have a 2-day workshop where we discuss the performance of the model. At that stage, we document the results, and the final stage of the workshop is essentially to look again at these top model problems and redefine them. If some problems have now been addressed, then the peg will be closed, and if there are new problems, it will be maybe decided that there should be a new peg, and we will try and find somebody to deal with that problem. Obviously, what we're really looking for then is implementation of the model configurations. And this is the stage at which you'd think the model is ready for implementation, but we try and start these implementation processes earlier so that we, even if it's fairly light, we start doing tests of the configurations when they're in the package testing phase. And the reason for this is that it allows us to identify problems early and possibly to influence what ends up in the final configuration based on some of these tests. For something like an NWP implementation, we may pick up every release or every other release and put that into our NWP suite. Again, our collaborators will usually pick up every other release. But for something like a CMIP project where you're looking at major upgrades from the previous CMIP, it's probably appropriate that this interaction should happen over a number of GA releases leading up to the freeze of the final climate model. So we're often asked how seamless we are, and hopefully I'll demonstrate this here. This is fairly small, this screen, but this is showing us at this range of resolutions that we run, and these are the parameters that we change when we run at different resolutions. So it's literally just the number of grid boxes, the time step, and sometimes 1 or 2 parameters within the physics as well, but we try and reduce these and limit these with time. And also they tend to be mainly at the very lowest resolution that will have something that changes with resolution. So the benefit of this is it's easier to increase the resolution in lower resolution systems. It can become almost trivial to do this because the model will already have been run at those higher resolutions in the past, so it's just a matter of testing its performance. We can also trust lower resolution simulations to tell us something about the higher resolution ones. This makes our testing cheaper, or if you throw that on its head, it means we can run more sophisticated testing with lower resolution systems to really try and understand the performance of the model. But the cost here comes in that more thought and care has to be taken when you're developing the initial science. So our developers here in our physics and dynamics sections will be thinking about that from day one. When they're thinking about their parameterization, they'll be thinking about how they can get it to perform across all spatial and temporal scales, across all of these resolutions. If it's something in the research cycle and it's been developed specifically for use at one resolution or specifically for use in one system, it means that there has to be additional work before that's seen as mature enough to come into our release cycle. In terms of different systems and complexity, we can obviously run the model coupled or uncoupled. I'm going to focus here on uncoupled atmosphere configurations or changes within the atmosphere. So we have a number of what we call system-dependent options. It's essentially up to the people running that system what they want to do. So an example here would be what calendar you use. Are you using a regular calendar or a Gregorian calendar? Are you running with moisture conservation on or off? So moisture conservation and energy conservation are options that we always put on in long simulations, but often don't have on if we're only doing a 5-day forecast. Aerosols is an interesting example here. So running climate run, we need a full aerosol scheme. That's relatively expensive and probably too expensive or possibly too expensive for short-range forecasts. But what we try and do is treat these as traceably as possible. And by this, we mean that we basically put together 3-dimensional speciated monthly mean climatologies based on the results from the climate model, and we feed that back into the model physics. So benefit here comes from the fact that this seamless configuration provides additional constraint, and depending on whether you're the person who wants to have trust in your model or the person who's trying to make a change, that can be seen as a benefit or a cost. I mean, it does make it harder to put some changes in, but what we've tended to find is it makes it hard to put changes in that improve the model for the wrong reason. And so when you do get these changes in, it will increase your confidence in the final configuration. What I see as the major benefit is this wide-ranging assessment that we do. It really improves our understanding of the model's performance, and the amount of effort that goes into that is significantly outweighs the amount of effort we could put into the assessment of any one system. When we're in the implementation, we'll get more information from those individual systems, and again, that will be collated back into the summaries of the entire assessment process. And the cost here is that it's harder to tune the performance for a particular application. So if you have one measure or one metric that you really want to improve in a particular system, it becomes harder because you can't just tune numbers in the model to get that number spot on. That can be beneficial in the long run, and what it means is that it stops you kind of tuning yourself into a corner where you tune your system so well that you can't make any change to it to make it better because you've got so many compensating errors within there. It may well be, and I'll come to this later on, that in some application of the model that you need to do a little bit of tuning or tweaking of something. But the point is that with this approach, you know that you've done that, whereas otherwise sometimes you don't know that you've done it. It increases the increased testing and stress improves the robustness of the model. This hierarchy approach to complexity means that extending the complexity of the model is simpler because the parameterizations have already been developed for use with a more complex system. But here the cost comes from the fact that the code can become more complex because of the number of use cases. And this requires a much higher level of governance and top-level control over the model's code. So we have a team whose job it is essentially to maintain and develop the code base. And one of their main tasks is to make sure when somebody's extending the code so that you can do something new with it, that it doesn't break existing applications. And that requires a lot of testing and work. So this is my final slide. This is focusing on the fact that I said before that you may want to tweak the model configuration for operational implementation. We try and do this as little as possible, but sometimes it's necessary. So what we have going down this line here is the GA trunk. This is GA 3, 4, 5, going down from one GA release to another. And this is essentially our best science. But we reserve the right to put together what we call a branch configuration. So if there's some particular aspect of performance that is struggling because of something we've put in the latest release or some ongoing problem with implementation of the trunk in some system, then we put together a branch configuration. And these are labeled with these point ones. So here we have GA 6.1, which is our current operational NWP configuration, and this has three differences from the GA trunk. It has an aggregated surface tile rather than tiling the land surface over 9 different tile types. There's one number different in the convection scheme, which is a long-standing difference between NWP and climate, and we have a difference in the sea ice, in one number in the sea ice as well. But the idea is, yes, we put this into this particular application, but when we're developing the model science, we make sure we develop on top of the trunk and not on top of the branches. And the other point is we should try, wherever possible, to build in changes to the trunk that means we no longer lead these branches. So these latter two changes here won't be leaded in future GA releases and NWP implementations. Another example of being pragmatic about this is our latest release, GA7, needed the inclusion of a new aerosol scheme, and the climatological version of this aerosol scheme that we need for NWP implementation isn't ready yet, but we decided that we would go ahead and freeze this because we needed to for CMIP. Also, the aerosol forcing of that model was seen as quite strong, and so a small number of changes to the cloud aerosol interactions needed to be built in to bring that back into a reasonable range, and so that's what's called the GA 7.1 configuration. It's that will be used in CMIP 6 and for the baseline of our next Earth system model. But again, in the development of GA 8, we're planning to overcome those issues so that all of these GA 7.1 changes are built into the trunk in the GA 8 configuration. So in summary, a unified model allows us to adopt a seamless approach to model development. I've focused here on the atmosphere because this is the area where I work and where we've pushed this to its conclusion. But we're starting to adopt this approach elsewhere. So we now have a global ocean configuration of the NEMO ocean model, a global coupled configuration, and we're starting to work our regional modeling groups on regional atmosphere configurations analogous to the GA. So hopefully I've highlighted significant technical and scientific benefits from this unified modeling approach, but also, as I said, there is some upfront cost to developing the model in this way. It's possible to make pragmatic choices during implementation whilst maintaining the integrity of the seamless trunk, and this is really a large part of what we have to do. We have to make sure that when we're doing this, that we're making these changes for the right reason and that we're not doing things that make it harder to continue developing that trunk. My assertion here is that once this approach has been adopted, then the benefits of the seamless approach significantly outweighs the costs. Thank you very much.
David, thanks so much. That was really, really impressive. So now I want to open it up to questions from the audience, both in the room and online. And to ask a question in WebEx, you can hover your cursor over the green tab that you see at the top of your screen. Actually, I don't think it's a green tab anymore. The tab at the top of the screen, click the Participants button, and then click the Raise Hand logo. And a hand logo will appear next to your name, and then I'll know that you have a question, and I can unmute your line, and you can ask a question. And I actually see that Mike Farah has a question, so Mike, I'm going to go ahead with you right away. So you are unmuted, so go ahead and ask your question.
Thanks. Does technology work? Can you hear me?
Yes.
Yep, I can hear you.
Yep. All right. Well, thank you very much. It was very good. My name is Mike Farah. I'm the director of the Environmental Modeling Center at the Weather Service. I've been in my new job for about 6 weeks, and I had a pretty small job. All they asked me to do was change the organizational culture that existed for 20 years and transition to a unified model and do it yesterday. So I want to talk to you about the latter one, that your unified modeling system. I did talk with Andy Brown, at least on the email, and we're going to organize a small visit to bring some of my guys out to meet with you all and try to see, not only to learn what you did over the last few years with your unified model, but to see how we could collaborate. You're going to be hearing from Cecilia, I think, next on the agenda about a system architecture that we're trying to build. So I got like 1,000 questions. I'll just limit it to one and save the rest to our visit. I'll save the rest to our visit. So the one I want to ask you about was your collaboration on how you do your model development. I see on one of your earlier slides, you list several other organizations that you collaborate with. So can you tell me, I guess specifically, what kind of mechanisms that you use to have outside, people outside the Met Office actually collaborate in the development of your new, your next model version, your branches or trunk, how you manage that, and so whether or not you would consider this a community model or just a tightly knit group of core super users that you allow access to your development code.
Okay, I'm going to do something now that I'm not sure. Can you still see my screen? Can you see the web browser coming up?
Yep,
I can.
You can see it.
Okay, I'm going to see if this works. Essentially, we use when this first happened, it was difficult. Our model was very tightly controlled. It was within our firewall. If you were outside the building, you couldn't see it. Even our collaborators next to university couldn't see it. And you can walk from here to there. And we have collaborators in Australia and in the US and across the world. So that, this really did cause a problem. And essentially, we've got to the point now, so I can try and multitask, where let's see if that works. We've got to the point now where we essentially host our model code on the web. Can't multitask. So basically, the code is hosted on the cloud. It's not in the building anymore. So if I go on here and I go to then this is the oh, is that not going to work? One more try. This is the homepage, and this is basically where we store all the code. We have all the documentation on here, and we have a single repository of the code that's visible here and to all of our collaborators. And the point here is we're not mirroring this out, we're mirroring it in. So when we build the model, we're taking the code from the cloud, we're putting together every 3 minutes inside a mirror that we can run from. But when I check out a version of the code and I check it back in, it doesn't go back into our mirror, it goes back into the cloud, and is visible outside the building almost immediately. And so we use this for developing the code, not just the code, but all the code that goes with it. But we also use it for developing our model configurations. So if I do this, is that going to work? So these are our global model development pages. And so if I go on here, then there's information here about the development of our next GA release. These are all the changes that we're trying to build in. And so we try as much as possible with this model development work to put the information out there. And so we have a kind of default of putting the information outside the building and only keeping it inside the building when it's necessary. So that's just the technology side of it. Of course, the difficulty then comes from the people side of it. You know, that's a lot more complicated.
Okay. All right. Well, listen, I don't want to steal the stage and everybody else ask some questions. I do have to drop off, so I really appreciate you taking the time to talk to us, and I look forward to getting with you and Andy and the rest of the group when we come out and try and do a visit later this year or early next year.
That sounds really good. I look forward to meeting you.
All right, and I'm extending the invitation the other way too. If you want to come out and visit us in College Park, let's talk about that as well.
That sounds really good.
All right, thank you pretty much.
Okay.
I think I'm done. You can unmute me or mute me again. So thanks again to all of you.
Thanks, Mike. Let's see. So we have a few questions. Ram, do you want to go ahead and ask your question?
Thank you, Heather. Good morning, David. This is Ramaswamy from Geophysical Fluidynamics Laboratory in Princeton, New Jersey. A very excellent presentation, and really delighted that you packed in a lot of information in a few slides very nicely. But I too have a lot of questions like Mike did, but I'll ask for just one. Could you comment on the strategy in place that within the unified modeling concept, how do you balance addressing key scientific questions that also go as deliverables to some particular set of customers and stakeholders versus the operational part, which of course also goes to a set, maybe the same set or even a different set of stakeholders and customers? I mean, in essence, the sort of unified model to deliver for more applications purposes versus something which is more direct for operational routine, like everyday forecasts.
Yeah, okay, so there's a long answer and the short answer. The short answer is with difficulty. The long answer is probably that, so if you have a very specific application and you have one customer base for that, and they have a major problem and it's their top problem, then you can make that your top problem as well, and that's obviously great. The problem with that is that there's only a limited number of people working on that to try and progress that particular problem. So what we try and do is when we put together what we see as the major problems of the model, we have different forums for pulling this in. So we have, forecasters in-house here. We'll get a phone call from them if they think there's something wrong with the forecast, or they'll arrange a meeting with us if they want to talk about something more systematic. They have a problem group where they meet to discuss what they think are their top problems as forecasters. They'll pass them over to us, and we then have to essentially assess with them and everybody else what we think, how we think that ranks in our list of problems and how they get prioritized. So out of these list of process evaluation groups, a couple of them will be to deal with specific model problems. Other ones will just have to be kind of pushed off to one side for maybe an individual to work on rather than giving it so much effort. But what we find in the long run is that, if we had one system, then we'd have far fewer people working on it, and we'd have far less resource to be able to deal with the individual. So in time, it means that you can address most people's concerns and most people's problems. But it takes a lot of understanding. It's like collaboration. People have to understand that their top problem isn't necessarily your top problem, but you have to understand how big a problem it is for them.
Okay, thank you. That's very useful.
Thanks, Ram. Are there any questions in the room here? We have a good crowd. Okay. Eric Baylor, do you want to ask your question?
Yes. I work with the Center for Satellite Applications and Research, and I've been working with trying to move towards coupled modeling as we bring in data assimilation and stuff. And my question is, for your models that are coupled with the ocean and the sea ice, are they two-way coupled or one-way coupled?
They're two-way coupled at the moment. So, the climate model, in terms of operations, then our seasonal forecast out is two-way coupled. We've done a lot of work on coupled NWP in the last few years, and we have a demonstrator suite in our operational suite at the moment. So it's low-resolution NWP model doing 5-day forecasts, and that's two-way coupled, atmosphere and ocean, using weakly coupled data assimilation. And our plans at the moment are to look at implementing an operational system to replace our deterministic models and our ensemble prediction system sometime in the next 5 years or so.
Do you perhaps know what kind of satellite data you're simulating for sea ice, if any?
In the ocean and sea ice assimilation, I'm not sure, actually. I think we're just using coverage data. I don't know where it comes from, so I think we're just using sea ice concentration. I don't think we have anything that tells us about the thickness of the sea ice at the moment. Yeah, I think that's right.
Okay, thanks. Just FYI, people like, for example, the University of Hamburg are starting to use SMOS data to establish thickness.
Okay. Yeah.
And they're combining both the cryostat and the SMOS for thinner sea ice and thicker sea ice.
Okay.
Great. Thanks, Eric. Hey, well, David, that was really great. Excellent discussion period there, too. And please, I hope you can stick around. And
yeah, I'll try my best.
Okay, great. Thanks so much for taking the time to present. Okay, so now I'm going to transfer control over to Cecilia. Cecilia, are you there? Should be unmuted.
I am
okay,
here.
Great. Okay, I'm just going to, while you get your slides up, I'll just introduce you. So Cecilia DeLuca is the head of the NOAA Environmental Software Infrastructure and Interoperability Group. And that's at Esrill in Boulder, Colorado. And the goal of this group is to advance understanding and improve predictions of the Earth system by delivering infrastructure software that enables scientific discoveries, fosters collaborations, and promotes resource efficiency. Cecilia's interests lie in the development of large, high-performance software systems and governance models that promote community and multi-agency ownership. She's an advocate for open-source software and developing shareable infrastructure for modeling and data services. Cecilia is the lead on many national and international software infrastructure projects in the Earth System Sciences, and these include the Earth System Modeling Framework, which we'll be discussing today, ESMF, the United States' premier weather and climate framework, as well as the Earth System Commodity Governance, or COG, and that's the collaboration environment connected to data services. Cecilia has a master's in engineering from Boston University and a master's in meteorology from MIT. Cecilia, thank you very much for joining us. And it looks like we can't quite see your slides yet. Have you been able to share the screen in your quick start?
So I don't actually see where share my screen is. Up there it is.
I think you just found it. Okay, great.
Okay, thank you.
Perfect.
All right.
Okay, go ahead whenever you're ready.
Okay. Thank you, Heather. So I'll give a quick introduction today to ESMF, the NOAA layer, and NEMS. I'll talk about the coupling infrastructure capabilities and flexibility that's needed to span weather to climate timescales. I'll talk about coupling in the NEMS unified modeling system, and then discuss open issues and next steps. So this intro to ESMF is going to be quick. It's just one slide. The Earth System Modeling Framework is community-developed software for building and coupling models. NOAA is a set of extensions to ESMF that increase component interoperability. And NEMS is one of the U.S. modeling systems that are using ESMF and the NOAA layer. So the little schematic at the bottom shows that ESMF is sort of a base layer of data structures and some generic utilities. The NOAA layer adds some standard behaviors to ESMF that increase the interoperability. And then at different centers, at NCAR for CESM, at NOAA for NEMS, at Navy for global and regional models, at NASA for Model-E and GS5. And for other modeling applications, we have some European groups using it as well. All of these groups use NOAA and the ESMF infrastructure for coupling, but they customize the solutions. So we'll talk a little bit about how that works. So ESMF and NOAA layer software infrastructure, they're used in modeling systems that span a range of space and timescales. So some examples are the Navy COAMPS system, which has a coupled atmosphere-ocean and supports a low-res global model with a high-res regional nest. It also supports a direct ocean-to-wave interaction, and that's used for weather and ocean prediction. GS5 is probably the closest thing that the U.S. has to a unified modeling system, or the one that maybe spans the greatest range of timescales. It is used for weather prediction through decadal timescales. It's structured as a hierarchy with more than 50 components, where a component can have subcomponents, There's a NOAA version of CESM that supports high-resolution ocean coupling for climate timescales with the typical CESM and climate components, which are atmosphere, ocean, sea ice, land, and they have other components as well, like land ice. The ESMF and NOAA applications, these that I just cited, along with some others, are described in more detail in a BAMS paper that just came out by Gerhard Torek. And I guess much of what this talk is going to be about is how these different predictive timescales can warrant different coupling strategies. One of the things that ESMF and NOAA do allow for are customization of coupling techniques for specific problems. So one example of a strategy geared to a specific predictive timescale is the exchange grid. So the exchange grid was developed at GFDL as a technique for accurate conservative grid remapping by Balaji and Jeff Anderson and others, much earlier than 2006, but that's when the paper came out. An exchange grid between two component model grids, it's the grid formed by the union of the bounding lines of the component model grids. So at GFDL, the exchange grid cell areas are used as the weights for conservative interpolation, and the surface flux calculation is performed on the exchange grid. What the exchange grid does is it really optimizes it really is the optimal use of the information that you have. It minimizes the need for extrapolation or interpolation. Another approach is to merge and compute fluxes in a hub coupler on the grid of one of the components being coupled. So in this model, there's sort of this central hub where the components are arranged around it like the spokes, and a variety of different interpolation methods can be used. And this is what CESM does, and that's described in Tony Craig's paper. So ESMF supports both exchange grid and hub and spoke style coupling. It also supports connections directly between components through simple generic connectors. But the main reason for using the exchange grid is to really get excellent long-term conservation. So this is something where when you have longer timescales, it's going to be a more appealing approach. There are also options for implicit and explicit coupling. So explicit coupling, and I'm sure all of you guys know this, but unknowns at the next time step are computed using known values from the time step before it. And in implicit coupling, unknowns at the next time step are defined by coupled sets of equations that include values at the next time step as well. So the solution requires either solving a matrix or an iterative technique. And the advantage of the implicit methods is that they allow for longer time steps and tend to produce more stable solutions, since the changes in the values they allow for smoothing further in time and space. The explicit methods can achieve potentially more accurate results with less computational effort for smaller time steps. So if you have something that's at a shorter predictive time scale, an explicit method might work better. ESMF and the NOAA layer support both implicit and explicit coupling exchanges, which is optimal depends on the science and goals of the application. But it also depends on the preferences of the center. So for the most part, CESM uses explicit approaches almost entirely, whereas GFDL, I believe, uses implicit coupling both for the atmosphere land interaction, where there are multiple land layers, and also for ocean ice interactions. So it depends on what you want to do scientifically. Another aspect that's another flexibility that's required for multi-scale coupling is flexibility in grids. So ESMF uses an internal parallel finite element mesh framework to implement grid remapping in a common 3D space. Originally, we did it with a native finite element mesh, and now we've been testing a DOE finite element mesh called MOAPP. And putting the grids into this common 3D space really enables ESMF to represent and remap virtually any grid. And this finite element mesh approach, which I think we had done rather uniquely except for the BOM codes, is now being implemented in the ACME project. So that they picked it up as the direction that they wanted to take as well. In addition to the flexibility to represent all of these different kinds of grids, ESMF also has options for how the lines are drawn between the grid points, whether you want straight lines or great circle lines, or even latitude and longitude lines, which are a little bit different than the great circle lines. So the infrastructure for supporting weather to climate scales needs this because it needs to be able to accommodate components that represent a wide range of physical processes, and potentially both 2D and 3D coupling interactions, particularly when you are looking at either hydrology or you're looking at ionospheric processes. So ESMF does this. Another area where flexibility is potentially needed is in interpolation methods. Excuse me. So it supports bilinear methods, higher order patch recovery methods, first order conservative methods. We have a higher order conservative method in the works, and that'll be in the next release, and nearest neighbor methods. But there are trade-offs in using these methods. So for example, the conservative remapping method introduces or tends to introduce larger interpolation errors relative to the patch higher order method, but it'll do a better job of preserving the integral of the data as it moves to the destination grid. So obviously it'll be more conservative. The choice of method may therefore depend on whether short-term accuracy or long-term conservation is more important. And again, that goes back to, the predictive timescale and potentially having trade-offs in what approach you want to use and whether you want to emphasize accuracy in the short term or conservation in the longer term. Okay, this is a little bit of a more technical aspect where there are a limited number of components in an application. Like in HWRF, for example, a hurricane model, you might just have atmosphere and ocean. The performance can be acceptable if they're always run concurrently on mutually exclusive processor sets. So they can be run as separate executables. But where there are more components in an application, so for in a climate model where you might have atmosphere, ocean, ice, wave, ionosphere, or more processes coming in, it's useful for performance optimization to be able to overlap components on the same processors or run them concurrently. And if the components are in separate executables, meaning they run as separate jobs, overlapping them becomes much more difficult. So US climate models that have more components like CESM or GFDL or GS5 tend to use a single executable approach. And that's generally what ESMF does, although it can also support multiple executables. And this approach of whether you, or this decision about whether you run components concurrently or sequentially also factors into how you combine the somewhat artificial splitting of the processes that occur in any model. So the implicit, explicit choices and the choices about resource mapping are also tied to decisions about how to advance coupled components. So you can either time split the coupling, so the two components are calculated sequentially, each based on the state used by the other, or you can process split, which means that two components are based on the same state and their tendencies are added to produce the updated state. So Williamson has a very nice paper on this from 2002. And more recently, there are groups, especially within DOE, that have been looking at the advantages of maybe breaking out maybe breaking out additional components in the physics. And that's been an active discussion in the community, I think. So process split coupling is associated more with explicit solutions and concurrent execution of components, and time split coupling more with sequential execution, where you're using the output of one process to feed the other process. So ESMF and the NOAA layer don't prescribe which approach to use. Again, this is a science decision, but it's also a coupling decision. I think this might be the final one. So another thing that is useful to have is flexibility in the run sequence. So ESMF and NOAA support flexible parameterized run sequences that are specified at runtime. And this means that you basically create this file that says what order you want the components to run in and what transfers between components you want them to make, and when you want them to invoke the mediator or the coupler. And there are examples here these are examples from NEMS of a hurricane sequence where you're just running an ocean and an atmosphere using a mediator to transfer data between them. And the global seasonal sequence is also shown on the right, which introduces an ice model as well. And the sequences are different. The components are called in different order, although both have a slow and a fast phase. And having the flexibility to be able to reorganize the sequences is very nice to have, and that can be important for the coupled system, or for a unified system. So when building infrastructure for weather to climate scale systems, there are many choices which have scientific and performance impacts. For example, which processes need to be able to run concurrently or on different grids? How should components be sequenced? Should we use an exchange grid for all timescales, for some timescales? Should we couple some components implicitly? Where and how should we compute fluxes? What interpolation methods and options should we use? And many of these decisions are not simple switches, but they're choices that require significant investment and development. So you can't say, for example, well, let's just implement everything and see which improves the forecast. I think some more foresight is required than that. So that brings us to NEMS. So NEMS is a rapidly evolving unified modeling system that will be the basis of operational modeling applications at NOAA. It is anticipated to include 10-day, 6-week, and 9-month forecasts. And so to become increasingly more seamless. Global and regional modeling applications are anticipated, and there are a whole host of coupled components that are planned for inclusion, including atmosphere, ocean, land, wave, sea ice, coastal, hydrology, ionosphere, and aerosol. And this is a little schematic of the applications that are anticipated over on the left, which include the weather, subseasonal, and seasonal applications that I mentioned, along with a space weather application, an ocean and ice application, and regional applications, including an air quality application. And they're all sharing the intent within the unified modeling system is for them to share components and infrastructure. So the current status is that we have initial prototypes of a seasonal system of a single domain regional configuration of a one-way atmosphere, upper atmosphere to ionosphere configuration. The hydrology and land is on a slower path than most of the others, so all we've really done there is bring the components in and demonstrate technical coupling. And lastly, there's a wave coupled one way to the atmosphere. It's atmosphere 2-wave, and those are all initial versions of all of those have been, again, prototyped. So currently, the NEMS implementation uses a hub-and-spoke architecture with explicit coupling, and it's a single executable. But the question is, in the long term, really, is this the right approach? And the evolution of the infrastructure for NEMS requires answering the questions that were posed earlier. You know, should we use an exchange grid, blah, blah, blah. Should we couple some components implicitly? where and how should we compute fluxes, what interpolation methods, and so on. And these are science questions. This isn't something that the infrastructure team can answer on their own. And they're science questions that really need to be answered by people who know a lot about coupled modeling. So to answer these and other questions, the system architecture team has been assembled by Mike, the new EMC director. And in addition to EMC staff, the working group engages experts in integrative science. And those folks have been pulled from GFDL, from ACME, from CESM, from NASA, from the Navy, and from other centers. Again, one of the big challenges is managing the trade-offs in the coupling between what a short-term prediction system needs and what a long-term prediction system, projection system needs. So that's what I had. Does anyone have any questions?
Cecilia, thanks so much. That was great, and I appreciate the questions at the end kind of for discussion. So are there any questions or comments that anyone would like to make online? Go ahead and raise your hand virtually, if so, and I will unmute you. And the other speakers, feel free to ask questions as well. And you are unmuted as well. Are there any questions in the room for Cecilia? Okay, I don't see any questions online. I don't know if David, if you have any comments, not to put you on the spot, but
so I guess I'm interested in the kind of single executable approach and the fact that the coupler can do implicit and explicit coupling between different components. I thought that was quite interesting. Our modeling system currently relies on very tightly coupled, implicitly coupled atmosphere and land, and implicitly coupled ocean and sea ice, and then we kind of run them in separate executables, and making sure that they're running, at reasonable rates together is always quite difficult.
Thank you. It's interesting to know that you like GFDL, also implicit coupling for atmosphere, land, and ocean and ice, unlike GCSM.
Yeah, that's right. I mean, it kind of shows where it's come from, really, because the coupled model is basically made up of those two things put together.
Yeah.
For us.
Thanks, David, for jumping in. And Cecilia, thanks so much. We'll see if there are any questions at the end, if you don't mind staying on.
Sure.
Oh, actually, I do see one question just came in from Frank Allman. Go ahead, Frank.
Sorry. Can you hear me?
Yes, that's the dog barking.
Yes.
Go ahead.
Are there any plans for ecological modeling?
Oh, that's a really good question. I think EMC would need to speak for itself with respect to NOAA. However, we're working with a German team that's doing ecological modeling using ESMF and NOAA, and they have a system that they've developed called MOSSCO, I think, M-O-S-S-C-O, where they're incorporating quite a lot of components together, and they do include ecological modeling. So it's not at NOAA, but there are people doing that using this framework.
Good. Thank you.
Thanks, Frank. Okay, thank you again, Cecilia. That was really great. I know it's early there for you. Well, actually not so early now. Thank you for joining.
Sure. Thank you. I do have another call at 9, so I do have to take off. But thank you for the invitation.
Thank you very much. Okay, so I am now going to switch over to Robert Pincus, who is the final speaker. And we can see your screen. Robert, can you, I'm not sure if you're on mute still.
No, I shouldn't be.
Oh, great. Okay. Let me just introduce you and find my notes. Yeah, Robert, thanks so much for joining in. Robert is a senior research scientist at NOAA Series, the Cooperative Institute for Research in Environmental Sciences in Boulder. Robert received a PhD from the University of Washington. Then he followed that up with a postdoc at NASA Goddard in the Climate and Radiation branch. He spent 2.5 years as a visiting faculty member at the University of Wisconsin, and then came to the University of Colorado in 2001. And Robert works on a range of problems with respect to radiation in the context of weather and climate, and his focus is mostly on clouds. And he is the editor-in-chief of AGU's Journal of Advances in Modeling Earth Systems. And he is one of the leaders of the World Climate Research Program, or WCRP's, Grand Challenges on Clouds, Circulation, and Climate Sensitivity. So Robert, go ahead whenever you're ready.
Well, so thanks, Heather, for the invitation to talk. It's always, yeah, slightly, I'm grateful. I also sort of curse you for having me follow these two very sweeping large-scale presentations.
I'm sure you can hold your own.
It would be hard to match. But I appreciate the opportunity to sort of advertise a code that is now at the end of a 3-year development cycle, and that I think we have a lot of reason to be proud of, and that I think will be useful across a range of applications. So the team working on this code is myself, and then a group of people at Atmospheric Environmental Research, led by Eli Malauer. Jennifer Delamere is one of the main contributors. We've been working in the context of a project I'll talk about later that involves people like Cecilia D, but also explicitly some folks at NCAR who provided some terrific feedback to us. So so I don't have a great visual for this, but I just want to say, of course, we're going to talk about a code that computes radiation for models of the atmosphere. And so the main application here is things like heating rates and surface fluxes, top of energy fluxes, and so on. And you need this code. You know you need this code. Just to sort of put it into context, radiation is the driver it's the fuel for the atmospheric heat engine. It's what drives the general circulation. So roughly speaking, because the equator is hot and the poles are cold, and that's because the sun shines at the equator. It's implicated in the propagation of the MJO. It's implicated in the structure of hurricanes, if you ask Greg Hakim. It's implicated in the development of shallow cumulus, even because it provides clear air radiative cooling at the top of the moist layer, provides a source of buoyancy for the development of shallow cumulus. So really the point here is only that radiation is involved in weather phenomena across a range of scales, from essentially the planetary to the shallow boundary layer. You'll notice that, so just to go back and forth, you'll notice that I'm looking at sort of across a range of scales in the next slide that's 2 orders of magnitude smaller, because I'm looking here not at the scale of phenomena, but at the scale of the grid mesh that one would be looking at. And the reason, what I want to explain here is that we use the same underlying radiation model, the same conceptual model, for essentially every prediction that we make. And that model has two sort of important assumptions in it. One is that it's plane parallel, and the other is that it's homogeneous. So what do I mean by that? I mean, plane parallel means the radiation goes up and down, and not side to side. And that doesn't need to be strictly true, but it means that you don't have a net exchange of radiation from one column to the next. So radiation is column physics. Is that appropriate? Well, the answer is yes, it is, certainly for dynamical prediction. And why do we know that? Well, we know that the sort of the mean free path, the distance that radiation travels, depends on the opacity of the atmosphere. In the clear air, those distances can be tens of kilometers, and this is affected, for example, the way we do the remote sensing of aerosol properties. But the atmosphere itself tends to be fairly homogeneous in clear skies across scales that are tens of kilometers. Whereas in clouds, the mean free path, the extinction is much higher, the opacity is much higher, but the mean free path is substantially shorter. So it's quite a fair assumption to make this one-dimensional radiative transfer assumption across scales going from sort of 1 kilometer out to 100, so grid sizes from the kilometer scale to the 100 kilometer scale. So that, I'll just remind you, this spans the range of scales that the Met Office Unified model scales. Some problems are introduced at some of the smaller scales. At the 1 kilometer scale, let's say, 1 to 5 kilometer grid mesh scale, you have two interesting problems. One is that the ground isn't flat. It doesn't all sort of face directly up into the sky. And actually, James Manners at the Met Office has done some really terrific work looking at this issue. And the other issue, which is that large mountains cast shadows. So of course, clouds cast shadows too, but they're not there all the time, so those shadows don't matter, and it's in quite the same systematic way. So there are issues with, but they primarily relate to the lower boundary when one gets to very small scales. At even smaller grid meshes, you have the problem of clouds, which of course are quite horizontally variable, and where clearly, I mean, you've had the experience of them casting shadows. You've also, if you were paying careful attention, would have the experience of radiation escaping from the sides and so on. It's not clear that this is relevant, though, for dynamical prediction. So the point really is that we can use a one-dimensional radiative transfer model essentially across any atmospheric scale to the best of our knowledge at this time. Where that's likely to fall down is in scales where we're not really busy making forecasts or predictions, but rather looking in more idealized cases. So that's nice because it means that we have column physics. It means that it parallelizes easily, and it substantially reduces the computational burden. So then you have the question of whether the homogeneity of the atmosphere is a good assumption. And I would argue that for scales less than a kilometer, or maybe slightly larger, that's sort of demonstrably true. And there's a technique that I and others developed about 13 or 14 years ago to treat the inhomogeneity that occurs in larger scales. So for example, if you have fractional cloudiness or clouds which are variable, and the idea there is that the radiation problem has a spectral, in the sense of the radiation spectrum, the frequency of the radiation or the color of the radiation. It has a spectral dimension, and so what you do is you draw samples that represent the inhomogeneity, as a way of representing the inhomogeneity, and you map those randomly onto your spectral quadrature points, your spectral integration points. And so that is a technique that's known as Monte Carlo independent column approximation, the ICA. And so really the point I want to draw out here is that the main difference between from a radiation codes perspective, between a large-scale application, a global application, and a small-scale, a regional or a highly refined application, is really whether one is doing sampling or not, because everybody's doing plane parallel radiation. The sampling, I'll point out, doesn't really affect the vast majority of what we do in a radiation calculation. So this means that we can have one code to rule them all, or basically one radiative transfer model that can be used across essentially all the prediction scales that we need to have. Not every radiation code is equally accurate, and this is from an assessment that we did last year, looking at a variety of models. Here we were focusing on climate models, so those participating in CMIT. The open circles are those models that participated in CMIT 5, and the closed circles are the current iteration of those models. The different colors represent different modeling centers' contributions, and there's 4 dots for each contribution because we looked at 4 different cases. The left-hand panel is the long wave, the right-hand panel is the short wave, and basically what you can see is that, and here we have a sort of a special case for radiation because we know the answer. We know the right answer. So our underlying knowledge of what the radiative fluxes should be like is based in reference models, often called line-by-line models, that can do can essentially remove all of the assumptions other than this one-dimensional assumption that I've described, and we can look at them in very carefully controlled circumstances, and we know these are very, very good. So we have, unlike most parameterization efforts, we have a reference. we can target that reference, and we can assess our parameterizations against those references. And that's what's shown in this figure. I'm showing you on the horizontal axis are top of atmosphere fluxes. On the vertical axis, there's surface fluxes. And so the diagonal lines are ISO lines of error in absorption. And so what you see is that, roughly speaking, that the magnitude of the errors in the long wave is less than in the short wave. Partly that reflects the fact that, just the fluxes in the long wave tend to be lower, but it also reflects the fact that the spectroscopy, the underlying sort of relationships between opacity of the atmosphere and the composition and temperature in the atmosphere, has been better established for longer with respect to the long wave than in the short wave. I want to point out that errors are present in some of these models that are enormous, 20 or 25 watts per meter squared in surface fluxes, much of that reflecting differences in the absorption of solar radiation. And these errors matter, as you might expect. This is a paper from Anthony DeAngelis that appeared last year in Nature, where he's relating the hydrologic sensitivity, so basically the rate of change of the surface precipitation as a function of the warming. And you can see that the models vary by a factor of almost 50% across them. So these are CMIP models. And that diversity, or the error, roughly speaking, error in the hydrologic sensitivity is primarily related to how sensitive the models are to solar absorption by water vapor. So what I've told you is that we can use the same code across a range of applications, and that the accuracy of that code has important impacts. That's, of course, also true for short-term forecasts. So with funding from the Office of Naval Research and this ESPC AOLI is the Earth System Prediction Capability, and then they're focused on coupling, so that's atmosphere, ocean, land, ice. Myself and the group at AER have been developing RRTMGP, where the P stands for parallel. And our intent is that this is a radiation code with sort of a decade-long lifetime. It's the successor to a code that's used in many of your models, I suspect. Certainly it's used across NOAA. It's used in CESM. It's not used, of course, in GFDL, where they have a ton of radiation expertise on their own and their own codes. But it is used at EMC. So that code is terrifically accurate, as has been relative to those reference models. This has been demonstrated sort of over and over. The things that we wanted to bring to that framework were efficiency, and here we imagined both modern computers and near future computing platforms. So we imagined GPUs and mics, and other coprocessors. But we also wanted it to be flexible, and we want that flexibility partly so that people don't have to make large changes in their code. For example, if they want to include scattering by clouds in the long wave, where it adds significant cost and adds marginal accuracy. But it also means across scales. So for example, if one's going to draw these McICA samples for models with relatively coarse meshes, or whether one will not in models that have relatively fine meshes, we wanted that to be as transparent as possible to the code. So these might seem like conflicting requirements. I want to describe to you how we have tried to resolve those conflicting requirements. So radiation parameterization, the steps are actually quite clear, and they're relatively small, and many of them are atomic in the sense that you can compute them in each grid cell independently of each other. There's also a spectral dimension to the radiation problem that is large. In our current iterations of RRTMGP, it's of order 250 in both the long wave and the short wave. So we have a large spectral dimension to work with. So you need to determine the spectrally dependent optical state of the atmosphere from its physical state. So the radiative transfer equation works on things like optical thickness and single scattering albedo. Those are the optical description of the atmosphere. But of course, the predictive models predict things like relative humidity, or humidity and temperature and gas concentrations. And so we need to be able to map the physical description of the atmosphere to the parameters that go into the radiative transfer equation. We need to do that for gases, and that's hard, and this is really where AER's expertise shines, I would say. So this is this is something which is sort of baked into our RTMGP. You need to do this as well for clouds and as well for aerosols. The distinction here, from our perspective, is only that the clouds, we expect you to use McICA sampling, and so to have this very finely resolved spectral dimension, where the aerosols we expect sort of a coarser spectral discretization. So you have to determine these spectrally dependent optical properties. From those, you have to determine the bulk properties of the layer, things like each layer's reflectivity and transmissivity. And then you have to compute the transport. And the difference between transport and essentially everything which has gone before it is that transport has a dependency in the vertical. So when one is computing the transfer of radiation, roughly speaking, I mean, you can do this sometimes as a matrix inversion problem, but there's a vertical dimension to it that means that it won't parallelize in quite the same way that the other pieces of the task can do. And finally, you need to take this spectrally resolved fluxes and you need to reduce them. So by which I mean you need to integrate over them typically to get a flux or a heating rate. You might also want to do some other more refined reduction that I'll talk about a little bit later. So we built a 3-layer cake. It was my wife's birthday last weekend, so I'm thinking about making cakes. Maybe that's where this tortured analogy comes from. The top layer is the interface, and this is where the flexibility arises. So the interface manages things like initialization. It manages things like error handling. So you, of course, have to give us arrays, and we, of course, have to be sure that you haven't made a mistake in giving us a negative pressure or a negative optical thickness. It manages things like the user choices. So you will tell us, or you will tell the code, whether you want to include long-wave scattering or not, or what degree of angular resolution you want in your scattering calculation, these kinds of things. And this interface layer manages that, and it also manages this mapping of the physical description to the optical description. So this is what takes a collection of input of varying kinds and maps it into our radiative transfer problem. We have a relatively thin layer below that we think of as being the broker, but it primarily does flow control. So it chooses different routines, roughly speaking, depending on the level of detail that's desired, both in terms of, how much fidelity do you want, how much computational expense do you want to expend on the solution, but also, have you, for example, broken out the aerosols separately, or are you doing a problem with no aerosols? Do you want clear sky fluxes, which are primarily useful for diagnosis, or do you just want heating rates at this radiation call? So we have this brokering layer, and beneath that, we have a set of computational kernels. And here, obviously, those of you who are involved in efforts to put things on GPUs, you'll recognize this terminology. What I mean is a set of very small, very highly optimized routines that do the computational heavy lifting. The inputs are sanitized. So what I mean by that is that the layers above have made sure that all of the dimensions, all the arrays are correctly dimensioned, all of the values make sense. And there's, for example, one routine which does the radiative transfer calculation, the transport calculation, when scattering is included, and a separate routine which does the calculation when scattering is not included. So they're very small. They do their job very well. They are bound to C. They have C bindings, and so that means maybe I'll talk about that in a sec. Sorry, let me just back up. So we have these computational kernels which can be highly optimized underneath, but we have icing as well on the cake, and that's data that we supply at runtime. And so that data includes the spectral discretization. So this is data here that relates primarily to the mapping of the gas that relates to determining the properties of the clear atmosphere from the gases and the temperatures and the humidity. But this determines the spectral discretization, and this determines sort of how many spectral quadrature points and so on. And that you drop in at runtime. So it means that it is very, very easy as spectroscopic data, for example, evolves. We can add this data in simply by giving you another file, and you do not, of course, have to change the code. I know, for example, the Met Office works this way. Previous versions of RTM, for example, did not. Okay, so this is how we have tried to arrange it. The flexibility, of course, comes in this top layer from the interface. The efficiency comes from highly tuned computational kernels, all of them vectorized over a column dimension, for example. So this is what I was just saying. This flexibility and some amount of this efficiency comes through the use of Fortran 2003 classes. And we recognize that this is going to be an adjustment for some modeling centers. We couldn't figure out how to get both flexibility and efficiency without doing it this way. So a class is similar to a derived type. Many models use these to package together related data. The difference here is primarily that one can package data and procedures. So that is to say routines that work on that data. And procedures have direct access to the data that's packaged in the type. So we require some classes for input. These, for example, are the description of the gas concentrations. They're the description of the spectral discretization, this so-called K distribution. These we've made opaque. You don't need to know very much about them if you don't want to. You can just think of them as being library calls, where maybe the big difference is instead of you call the library, but then you pass a variable that's associated with the library to our routines. So we use a bunch of these. Outputs are an extensible class. So we have provided the facility to do the things that most people need to do broadband heating rate, to do broadband fluxes up and down, to compute net fluxes up and down, and from that to compute heating rates, although we consider heating rates to be a thermodynamic calculation, and you probably ought to do it yourself from the fluxes. But so we know that that's what people will need. We have added the capability to do this by this band, roughly speaking, the coarser of the spectral discretization. But you may want you might want, for example, photosynthetically active radiation at the surface to feed to your land model. So what you do is you take our code and you extend it. You write a very short piece of code that sits on top of ours that will be invoked by RRTMGP, but where you don't have to, for example, plumb in a line that says here is where the output comes for photosynthetically active radiation. So this is something that you have control over, where you have access to the full detail of the model. So all of the fluxes at all of the spectral points at every grid cell, and you can choose how you would like that reduced, that data volume reduced, to give you the information you need in your particular application. We recognize that people don't like this. I know this is not allowed, for example, or it wasn't 2 or 3 years ago allowed in the Met Office Unified Model, this idea of extensible classes. What they are, they're USB plugs. I guess that everybody that's listening to me is within arm's length of a USB plug. And that is a standardization. That's a way of saying this is the interface that we have between one kind of hardware and the other. And we acknowledge that there's different applications. The USB plug will charge your phone, but it'll also read your hard drive. That's what we're trying to do with these extensible classes. It gets freakier, or maybe let's just say more unusual. We've provided 2 ways for you to give us the aerosol and cloud information that you need. So you can provide it directly by giving us spectrally resolved and McICA sampled optical properties. So one wrinkle here is that these optical properties need to be bound in a class that we have defined, which is roughly, we have 3 flavors of it. One of them corresponds to the optical properties you need in a calculation where you don't include scattering. So that would be most useful in the long wave. One of them when one includes 2-stream scattering, and one of them when one includes N-stream scattering, where we have yet to implement any of those solvers, but we imagine sort of doing 4-stream calculations. And so you have to provide this data in a package that we have created for you. But the alternative, and this is useful potentially for efficiency, is you can provide us an object where we've not, an object that describes on the one hand, the cloud optical properties, and on the other hand, the aerosol optical properties, where you package the data you need and the function you need to turn that data into the spectrally resolved optical properties. This helps with efficiency. So it's a real step forward. We're using these so-called abstract classes, and we recognize that this is really not done in any model that we have ever worked with. But it will allow the data transferred between RRTM, between the radiation component and the rest of the model to be minimized, because the amount of data you need to describe the physical state of the atmosphere is substantially smaller than the spectrally resolved optical data. So we don't know whether anybody will use this. We hope so, but we'll see, I guess. Okay, so our code is essentially done. I wanted to say that RRTM-GP as a package comprises two things. It comprises the code, but it also comprises this data. And so you can think of new data as being updates to the science, to the spectroscopy that we need. The code is mostly done. We have to begin really stress testing it and try to break it, and that will no doubt expose bugs. But certainly the interface layers and the sort of layout is essentially fixed. It won't really be useful until the new spectroscopic data is available, and that I would say we expect by the end of this calendar year. So for modeling centers that are interested in exploring this, we are open to collaboration. We've been working with NCAR, as I said, and there's an initial implementation in the NCAR CAM. And feedback from them has led to some architectural changes on our side, some changes to the interface. So this code is available for you to look at, to start working with, but you can't use it until probably the end of the year. That's what I have to say.
Great, Robert. Beautifully presented and great analogies, and I am hungry for cake now. So for those of you online, go ahead and type in a question into the chat box or raise your hand virtually, and I will call on you.
Oh, sorry, Eli reminds me offline that actually the spectroscopic bunches of this has also been funded by NASA. I should not forget them.
Okay. So, yeah, we can see your screen, Robert. Keep that in mind. So maybe I'll take away your sharing.
Oh, no, sorry.
That's okay. Okay, so I don't see any questions. So, David, I've unmuted you in case that I'm putting you on the spot yet again, but feel free to make any comments or ask any questions. We're right about the end of our time, so looks like there's nothing coming in, so I guess I'll just thank the three speakers again for really, really excellent presentations across the board. Thank you so much for joining, and the recording will be online very soon, and the PDFs as well. So thanks everyone for joining today, and keep your eyes out for the webinar coming up in October to be announced soon. Okay, so we will see you next time. Thanks.